All right, so our next topic in space exploration is topic 2. It's called Stronger Eyes and Better Numbers. So it was telescopes and the invention of the telescope that allowed astronomy to make a big leap forward. So a telescope, it's used to magnify objects at great distances. A simple telescope magnifies objects. It has an objective lens and an ocular lens. The objective lens, it's the large one at the front of the telescope. The ocular lens is the eyepiece through which you view the magnified object. So here, this is a parts of a refracting telescope. Here we have our eyepiece. Here, there's the ocular lens. And then here is the objective lens. The incoming light is coming from here. Okay. So a couple of people we're going to talk about today. Hans Lippershey. He was a Dutch spectacle maker, and he invented the telescope in 1608. And so what he noticed was that a magnified image is produced when certain lenses are placed in front of each other. So then later, Galileo Galilei, he later improved the telescope. He was an Italian astronomer, so he basically built on what Lippershey discovered. And then his observations revealed details of the celestial bodies that required new explanations. So here, so the earliest optical telescope we know of was made in 1608 by Hans Lippershey, and then he publicized his designs, and then those reached Galileo Galilei, and then when he heard of that, then he built his own. So this is a statue of him, of Galileo Galilei, in Spain. All right.
But he deserved his statue.
So here are some observations that Galileo observed. So here he was able to observe the moon's blemishes. He saw the shadows. He was able to see that those shadows, they lengthened and shortened with the sun's angle on them. So he was able to conclude that the moon's surface has mountains and craters on it, similar to Earth. Here he was looking at the sun. He observed the sun had spots on it, and over a period of about a month, those spots, they would move across its surface. Then they'd disappear, they'd reappear again on the other edge. So he concluded from those observations that the sun rotates on its axis. Here he was looking at Jupiter. He was able to see 4 small stars that move back and forth across Jupiter. So he concluded that Jupiter had 4 moons. So here, this photograph is showing 3 of the moons that Galileo saw. Here, when viewing celestial bodies through his telescope, Galileo observed that the planets were disc-shaped. He saw the planets in some detail. The stars were still pinpoint in appearance, so he was able to conclude that he couldn't see the stars with more detail by using his telescope, so that led Galileo to believe that the stars are much farther away than the planets. Okay, so then Galileo...
Sorry.
Okay, so Galileo approached inquiry in a different method. So he insisted that the adequacy of models, it should be assessed with observations. So his observations supported Copernicus's sun-centered model and not Ptolemy's Earth-centered model. So he also saw that Jupiter's moons orbit Jupiter but not Earth, whereas the Earth-centered model, it assumes that all celestial bodies orbit Earth. And then because Jupiter's moons orbit Jupiter and not Earth, it became more and more clear to Galileo that Earth is not at the center of the universe. All right, so here in this scene, in this picture here, we're seeing he's using his telescope. He spotted 4 moons. They were orbiting Jupiter, so therefore not everything revolved around Earth. All right, scientists have found now that Jupiter has 17 moons. So next with telescopes is its resolving power. So this determines the fineness of detail a telescope can produce of an object in view. It depends on the diameter of the objective lens. So the diameter of the circle. A larger diameter objective lens, it will produce finer detail when viewing. So larger diameter objective lenses are what increases a telescope's resolving power. Okay, so this would be a wide telescope here. Next is refractors and reflectors. So a refracting telescope, this type of telescope has a lens for the objective. So here it's a lens. And then a reflecting telescope, this one is going to have a mirror for its objective lens. This is the eyepiece here. This is the mirror here. So that's the big difference between refracting and reflecting telescopes. So next, Isaac Newton. I'm just going to pause here one sec. All right, so next, Isaac Newton, he designed the reflecting telescope to overcome the problem that early refractors could not. They could not focus different colors in the same place, but mirrors were able to. So later, that problem was solved for the refractors, and both types of telescopes are in use today, sometimes in combination. Refractors give better images than equal-size reflectors, but reflectors can be made much larger. But new designs, they have elements of both types of telescopes. So here we have a refracting telescope. There's the objective lens, there's the eyepiece. And then this is a reflecting telescope. It's going to have a mirror, a secondary mirror. Oh, sorry, the mirror is here. There's a secondary mirror, and then the eyepiece is like this. And then this is a combination telescope. It uses a combination. All right, so again, refracting telescopes, they have a lens for the objective. Reflecting telescopes, they have a mirror for the objective. And then combination telescopes, they'll have a lens at the front and an objective mirror at the back. All right, so I'll pause. All right, so that was a little bit about the 2 types of telescopes. So next, Copernicus's sun-centered revolution continues. So Galileo's telescopic observations, it helped to confirm Copernicus's sun-centered model of the universe, but it still needed some work because Copernicus's model was still using those epicycles for the planets, just like Ptolemy's model. So then came Johannes Kepler, a German mathematician. So in 1609, he found the answer to this problem. So he was a mathematician, so he did a lot of calculations. So his predictions of the planet's motions were more accurate because he predicted that the orbits were elliptical, not circular. This is an ellipse shape. It's like an oval shape. So it kind of looks, an ellipse kind of looks like an oval shape or like a squashed circle. So planets in the solar system, they move in elliptical orbits around the sun. So Kepler was able to find the shape of the orbits, but he also figured out the shape and scale of the entire known solar system. And lastly, we're talking about universal gravitation. So the law of universal gravitation, so Newton's law, states that all objects attract all other objects, and that provides an explanation for the planet's elliptical orbits. According to Newton's law, there is a gravitational force between all objects, okay, that pulls them together. When there's no forces acting on an object, it's going to move in a straight line at a constant speed. The planets are always moving, they would fly off through space in a straight line if there was no force acting on them, right? So it's the force of gravity that's pulling them in towards the sun, and that's what's balancing their tendency to move in a straight line. All right, and that is the result. It's an orbit for each planet. Okay, so here's the planet. They would tend to move in a straight line, but we have that force of gravity that's pulling towards the sun, and therefore we see those elliptical orbits. All right, so I have one last video here, Crash Course History of Science.